There are two more theorems given in your textbook in this chapter. The one I've got up on the board right now is Theorem 2. The name Theorem 2 is specific to our textbook. It is not important that you remember that it's Theorem 2. It is important that you understand the result. Okay. So this is saying if I have two functions, f of x and g of x, and they have this relationship, f of x is less than or equal to g of x. So I'll refer to f of x as the smaller function. Okay. And that relationship holds near a, except possibly at a. Because remember, if we're taking limits as x approaches a, the limit deals with what I expect based on the nearby behavior. Don't care what, if anything, happens actually at a. The limit is all about what I expect based on the nearby behavior. And so this is telling me what that nearby behavior is. That close to a, f of x is the smaller function, smaller or equal to. Okay. And then if both of these limits exist, then the limit of the smaller function will be less than or equal to the limit of the bigger function. Not hugely surprising. Let's just take a quick look at something. Let's let f of x equal negative x cubed over x, and let's let g of x just be the constant function 0. Okay. Now, of course, this simplifies. This would just be negative x squared if x isn't 0. Okay. And so I will have the case that f of x is less than or equal to g of x, because it's going to be strictly negative close to 0. Actually, it's going to be, and this inequality actually holds everywhere except at 0, where f of x isn't defined. Okay. Now, if I take a look at the limit as x approaches 0 of f of x, that's of course the limit as x approaches 0 of just negative x squared. Okay. This function, without that restriction, isn't the same as negative x cubed over x, but they have the same limit because they're the same near 0. So this would just be 0. And then the limit as x approaches 0 of g of x is just 0, because the limit of a constant is, of course, a constant. Okay. Not super surprising. Now, I picked an example here where we got equals. It is important that this applies with inclusive inequalities. Even if this was a strict inequality, this needs to be an inclusive inequality. Then I just draw the functions that we have here. I'm going to try to use a marker that writes. So here's my g of x. That's the function 0. And f of x was this function. It was negative x squared, except it wasn't defined at 0. So it was actually always the case that f of x was strictly less than 0, because it wasn't defined at the one place where they would be equal. But yet the limit, as we approach 0 of f of x, is equal to the limit as we approach 0 of g of x. So it's possible for one function to be strictly smaller than another, but yet as you approach a certain point, they're approaching the same value. That's what I really wanted to emphasize here. Of course, it would certainly be possible as well for the limit of the smaller function in some cases to be strictly less than the limit of the bigger function. But it is possible for those limits to actually be equal. I've got one thing is smaller than another, but they get closer and closer and closer together so that they have the same limit at some point. Okay, we're going to use this in the next video to build up to a theorem that in your book is called Theorem 3, but it also has a real name. It's called the squeeze theorem.